All right, so what we're going to be looking at today, okay, are the ways that energy is transferred on Earth. First off, how it gets here, okay, where it comes from, kind of what happens to it, and then, like we said, the big thing here is how is energy transferred from place to place on Earth. Okay, so understand the three parts of the Earth. Okay, there's essentially like the Earth's divided into like three spheres, which is odd because it's only one sphere, but there's three. Okay, understand how energy on Earth is absorbed, used, and reflected. Those are the three things that can happen to sunlight when it strikes the Earth's surface. Okay, it can be absorbed, which essentially means if you absorb energy, what's going to happen to your temperature? It's going to go up. Okay, the Earth can absorb energy from the sun. Okay, some of it gets used. Okay, we might also use the word converted. What's the only process that directly converts solar energy into chemical energy? Photosynthesis. Okay, so there's only one group of organisms that can actually carry out this process, and that's the plants. All right, the last thing that can happen, and then a lot of it does happen, is reflection. Okay, a lot of the sun's energy reflects off of various parts of the Earth. Okay, either it reflects off the atmosphere before ever hitting the surface, or it reflects off of the surface of the Earth when it gets here. Okay, now, does the amount of energy that gets reflected vary? What kind of things could affect how much of it gets reflected? Okay. Right, the type of terrain. Okay, essentially the color of the surface. Okay, snow is a huge reflector of solar energy. Right, right now we've got lots of it. Okay, and so any sun that comes down is certainly not reaching the ground. Okay, it's hitting the snow and it's reflecting off. Okay, light colors are good reflectors. Okay, white is the best reflector because white reflects all wavelengths of light. Okay, everyone follow me there. Conversely, black absorbs all wavelengths of light. Okay, which is why if it's a hot day in the summertime, okay, a black car or a white car, okay, they will have different temperatures because the black car will absorb far more solar energy because of its dark color, whereas a white car will stay cooler for much longer. All right, everyone follow me on that one. Okay, if you got a dark leather interior, okay, you probably had that experience. Okay, you get in and you're wearing shorts and you burn your legs. Okay, on the interior. Okay, it's not as bad with leather. Okay, but back in the day when they made seats out of vinyl, okay, we had a '68 Ford Galaxy when I was a kid. It had vinyl seats, black. Okay, and they had little metal things for some reason as like patterns in them, and you would sit on those and you would get a little burn on your leg. Okay, it's like a 4-year-old kid. Yeah. Okay. And I just dated myself saying I had a '68 Ford Galaxy. I know. Okay, all right. Understand how the energy and the Earth interact to produce the conditions necessary to support life. Okay, so how do all these things work together, okay, to essentially make energy available, okay, for life to exist? All right, first sphere, okay, first part of the Earth we got to talk about is the atmosphere because it's the first part of the Earth that solar energy interacts with, okay, on its way here. Now, obviously, it's a layer of gases. I'm never going to ask you about the names of the layers. Okay, you probably know them, but okay. We live in the troposphere, okay, which is the thickest part of the atmosphere, closest to the Earth. Okay, there are other layers of it, okay, that are there, but we're not too concerned about them. All right, the innermost layer, the one we live in, extends to about 11 kilometers, okay, above the surface. Okay, 11,000 meters. All right, you get out of that, and you're starting to get into the troposphere. Right. Now, 11,000 meters, guys, is very, very tall. There are only 2 points on Earth that you could stand on that would essentially be outside of that. What are they? Mount Everest and K2. About the only 2 places on Earth you could stand where you might be in the beginning of the stratosphere. Can you live on the top of those 2 places? For a short period, yes. For an extended period, no. All right. Reason being, there's not enough atmospheric pressure there. It's not that there isn't enough oxygen. Certainly that's a problem too. Okay, but you can climb to the top of those mountains without oxygen. The problem is that there's not enough atmospheric pressure. And what happens is you begin to lose gases through your body. Okay, a certain amount of pressure is needed to keep gases dissolved in your blood. Okay? If that pressure is not there, the gases come out of your blood. They cease to be dissolved in the blood and they become gases again. What will that form? Bubbles. That may not sound like a big deal, but it is, because bubbles are gases under pressure. And if they are inside of your blood vessels, the pressure they can exert can be very excruciatingly painful. That's what the bends are. Okay, has anyone ever had the bends? I haven't either. Okay, but apparently they're very, very bad. All right, and if you get them, they have to put you in one of those big hyperbaric chambers. And if you're claustrophobic, it would be your worst nightmare, right? Because it's like coffin, and they put all kinds of atmospheric pressure on you to force the blood and force the gases, sorry, back into your blood. Right? On the top of Mount Everest, the worry here is that there's not enough pressure there, so you're losing these gases, but you're also having a problem with keeping fluid where it's supposed to be. Okay, and fluid will begin to build up in your lungs, and you'll start coughing, and you can get pulmonary edema. Okay, which basically means fluid builds up in your lungs and you cough until you die. Okay, yeah, so it's generally bad. You can drown in your own fluid. Okay, so pretty bad stuff. Right, yeah. Usually scuba divers have more of a problem with the bends than climbers do. Climbers have a problem with the other problem, which is pulmonary edema, okay? Which is why typically they carry syringes full of cough suppressant, okay? The same stuff that's in like Buckley's and Vicks and all that kind of stuff, okay? It's called dextromethorphan, right? They take syringes of that, and if they start to get pulmonary edema, they'll inject themselves so that they don't cough, okay, as much. Because if they start to cough, they can actually cough enough that they'll rupture the linings of their throat and trachea, and they'll bleed into their lungs, which exacerbates the problem, obviously. Okay, so atmospheric pressure is a big deal. We need to be down here where the atmospheric pressure is proper. Okay, as you get higher up, you can start to develop problems. Okay, stratosphere, obviously quite a bit thinner. Okay, not a good place for us to be for extended periods. Okay, and that's typically where jets and stuff will fly. Okay, ozone gas is present in the stratosphere. That's where the ozone layer is. Okay, is in the stratosphere, and it shields us, okay, from many of the harmful wavelengths of radiation that come from the sun. Okay, especially ultraviolet light. Okay, but it also helps to deflect things like X-rays and gamma rays and stuff like that that are also very, very bad. So if you spend a lot of time at high altitude, you actually get a lot more radiation than you do lower down. Okay. Airline pilots and flight attendants are actually at higher risk of cancer, okay, than a person who works at ground level all the time. Okay, because they are consistently above that level where they're exposed to more solar radiation, and it can go through the skin of an aircraft like a hot knife through butter. Okay, so you don't notice it. You don't notice it, but it's coming through. Okay, so the atmosphere plays some important roles. It also plays an important role in that it can help to transfer thermal energy from place to place, and in fact, it is most responsible for that, more than any other part of the Earth. The atmosphere transfers thermal energy from place to place because it's the most fluid and it touches every single place on Earth. Okay. All right, so atmosphere and climate. So we got solar radiation coming in. Okay, so we got the sun here. It's obviously not that close. Okay, it's not to scale. Okay, so it's coming in here, and some of the solar radiation will get scattered by our atmosphere. What effect does this scattering produce? It makes the sky blue. Okay, the fact that violet and blue lengths of light are scattered by the composition of gases in our atmosphere is what makes our sky blue. It is not because it reflects off the ocean. I know somebody told you that somewhere along the way, but the last time I checked, water is clear. Okay, the ocean looks blue because it reflects the sky, not the other way around. Okay, so we've got radiation getting scattered, visible light being scattered by the atmosphere. Okay, really bad shortwave radiation also being reflected away by our atmosphere and deflected by our magnetic field. Okay, then we've got some stuff coming down and it gets reflected off of the surface. Okay, so that happens, but it doesn't all go straight back out into space. Some of it gets trapped by what? By CO2 and other greenhouse gases. Is that bad? People aren't sure about that. It's good. Okay? If we didn't have a greenhouse effect, the Earth would be an ice cube. All right? It would be an absolute ice cube. We need some greenhouse effect in order to stay warm. We need some of this thermal radiation that bounces off the Earth to be reflected back down. right, and make a couple of trips here and there so that the Earth has more chance to absorb it and stay warm. Do we want it to get out of control? Absolutely not. That would be very bad. Okay, we see an example of that in a nearby neighbor. Which planet has that problem? Venus. Okay, Venus's atmosphere is so thick, okay, that it could crush you. Right? In fact, it could crush submarines that can go down to the bottom of the ocean. There's that much atmosphere there, and its composition is almost entirely carbon dioxide. So any light that comes in doesn't get back out. Right? And so it's, hundreds of degrees Celsius on the surface. It's not going to get like that here, okay? But obviously that's kind of the runaway effect. Right? We've got a good greenhouse effect going, okay, where it keeps our Earth nice and warm. Okay, so we've got some energy obviously gets absorbed by the Earth, okay, and some of this absorption could also be that conversion that we talked about. Okay, some of that absorbed light is actually being absorbed by plants and converted into chemical energy, and that is the start, okay, of energy powering all life on Earth. Certainly, life on Earth needs thermal energy. We got to stay warm, okay, but most importantly, life on Earth runs on chemical energy, on glucose. Okay, all living things require that. Okay, and this is the most important step in making that go. All right. So incoming radiation is reflected away by particles in the atmosphere, water vapor, ozone, etc. Okay, and by this. Okay, this term is really important. Albedo. Okay, albedo describes the reflectivity of the surface of the Earth at any given point. Right now, okay, the albedo of the surface of the Earth here, where we live, is very, very high. Okay? It is highly reflective because it's covered in white snow. Right? In the summertime, okay, it's much less reflective because it's, we got stuff that's green, it's absorbing a lot more. Okay, we got colors that are more absorptive than they are reflective. Okay, and we can see that kind of in this diagram right here. Okay, so here's your typical, okay, kind of northern hemisphere kind of situation. We got the sun in the summertime, 70%, okay, of the energy coming in that gets through the atmosphere is being absorbed by the ground. Okay, 10% of it is reflected off of water, and 20% of it is reflected off of various surfaces. Okay, so high absorption rate in the summertime, and that leads obviously to higher temperatures. Okay, in the wintertime, 85 to 90% of energy striking the surface is reflected. Okay, that's how much different the albedo is, okay, when there is snow cover. All right, so only 10 to 15% is absorbed, so it's almost completely flip-flopped, okay, between summer and winter. So does that make snow a good thing or a bad thing? It's not really good or bad, but snow can be a very good insulator if you are under it. All right, how many people have ever built a Quincy before? Come on, you guys got to get a life. Quincy's are fun. I build like 4 or 5 a year. My kids love it. Okay, yeah, how do you build a Quincy? It's really easy. Make a big pile of snow, then hollow the pile out and crawl inside. Yeah, that's a Quincy. Okay, okay, so you have made one. Good. Okay, I take back any previous insults to your lives. Okay, all right. So why does a Quincy keep you warm? Well, first off, it's white. And white reflects thermal energy. So if you crawl inside, any energy that you're radiating away, and you are, okay, is reflected back to you, right? Or at least 85 to 90% of it, right? The other reason is that snow is a good insulator, right? Snow is not, it's the solid form of water, but it's crystalline, and the crystals are very small. And when you pile them up, you make them interlock. When they interlock, they create spaces in between, okay? So snow looks a lot like fiberglass, okay, the pink stuff that's in the walls of your house. Okay, there's air that's trapped inside of it that can't move, and when air can't move, it can't transfer energy. It's stuck there. Okay, so it acts as a good insulator, a good reflector of your energy. So if you're ever stranded in the woods in the winter, okay, build yourself a Quincy. It doesn't take very long. You just need to make a pile of snow and then hollow it out. Okay, you could even do that with your bare hands. Well, not your bare hands because they get pretty cold, but your gloved hands would work better. Okay, everybody with me there? All right. Okay, so gases present in the Earth's atmosphere help to maintain the Earth's temperature. Carbon dioxide is obviously the main, one of the main greenhouse gases. Okay, chlorinated fluorocarbons. Okay, methane. Where does that come from? What's that? Yes, yes. Herbivore farts, okay, make methane, all right, and so do many types of bacteria called methanogens, okay. Ozone, okay, ozone is part of that as well, okay. Nitrous oxide, there's not very much of that, okay. And one of the things that's not listed there, and oddly enough, is present in large amounts, is water vapor. Okay, water vapor is also a greenhouse gas. All right, so what it does is essentially keeps some of that energy from just going out into space. Okay, the Earth is really a big mirror, right, in terms of solar radiation, and that's why you can see it, okay, from other planets. Recently, the Cassini craft that's orbiting Saturn took a picture of Earth from Saturn. Okay, the Voyager probe also did it. Once in a while, NASA gets the opportunity to take a picture of Earth from somewhere else, and they always take it when they can do it. Okay, to see what our little planet looks like. Okay, it's a tiny, tiny little blue dot. Okay, why is it there? Because it's reflecting the sun's energy back. Okay. All right, this picture here, I just found it the other day, so I wanted to illustrate it here. This is kind of showing that rain shadow effect we talked about before Christmas. Okay, this is Mount Robson. Okay, and when you have water vapor in the air that's as a vapor, as it comes in here and it gets pushed up and over, its temperature drops, we said, and that creates that rain shadow effect where all the precipitation falls on this side and none of it gets over here. Well, you can really see with Mount Robson, lots of times it's very clear, and then all of a sudden a cloud forms right over top of the mountain. Okay, and it's just because a moist air mass has moved towards it and gotten pushed up and over. And as it gets pushed up and over, it condenses, and the top of it gets a little fresh dusting of snow, even though all around is blue sky. Okay, so this is kind of a isolated rain shadow effect, just so you can sort of see the cloud forming and how the cloud dissipates, okay, as it gets over to this side. It's lost all the moisture over here. All right, the hydrosphere, second part of the Earth. Okay, we said the atmosphere is most responsible for transferring solar energy, okay, because it's the most fluid. Okay, gases are a fluid, make no mistake. Anything that can flow is a fluid, and gases can flow. All right, the atmosphere touches everywhere on Earth, and it moves most easily. Now, is the hydrosphere also fluid? Yeah, it's all the water on Earth. But is there water everywhere? No, a lot of the Earth is water, okay, but it isn't everywhere. And even though it can only move kind of in the places where it's located, not like the atmosphere, which is everywhere. Does everyone kind of follow me there? So yes, the oceans, okay, and all the water on Earth are important in terms of transferring energy, okay, but not as much as the atmosphere is. Okay. Now, one of the big things that the hydrosphere transfers is this stuff. Okay, we're going to talk about it a little bit more later on here, but it's latent heat. It's the heat that goes along with water vapor. In order to get water to be a vapor, what has to happen? What does liquid water have to do? Yeah. Evaporate, right, okay? It has to evaporate. Does that take energy? It does. And when you evaporate water, okay, you give it extra energy. We call that energy latent heat. It's not temperature, okay? It's not kinetic thermal energy. It's potential thermal energy, all right? And so if a whole bunch of water evaporates and then moves from that place to another place, when it condenses and falls as rain, it doesn't just provide moisture, it also provides energy. Because when it condenses, it releases all of the energy that it gained in becoming a vapor. All right? When it releases the energy, it's transferring it to that new spot, transferring thermal energy to that space and warming it up. Everyone with me there? Okay, so the hydrosphere, because it contains the water, okay, is a big part of moving or of providing latent heat. The atmosphere is still the mechanism that moves it from place to place. Okay. All right, so all the water on, above, or under the Earth's surface is the hydrosphere. Okay, that can be water vapor, liquid water, even ice. Okay, it's water in any form. Less than 0.1% of all the water evaporated from the surface of the Earth is returned to lakes, rivers, or streams, or seeps into underground hollows. The rest returns to the ocean or is frozen in the polar ice caps. Okay, so if we had a really hot day in the summertime and a bunch of moisture evaporated, only 0.1% of that would come back to exactly this spot. The rest of it would be somewhere else. Okay, it would move, it would rain out somewhere else, end up in a river or stream, okay, and head to the ocean, which is fine, because where does most of the moisture we get come from? Where most of the moisture is, the ocean. All right, so it eventually comes back here. It just doesn't, the water that evaporates from here doesn't come back here. You get that impression when you look at diagrams of the water cycle. It's like, oh yeah, water evaporates and then it rains and it's like it all stays right here. Okay, but it doesn't. It's a far more complex system than that. Okay. All right, how many times have you seen this? Like every year since you were in grade 3, right? One more time. Okay? It is the last time that you will go over this, but you have to go over it one more time. Okay? So, water cycle, pretty easy. Okay? Water can evaporate, obviously, from the ocean. It can evaporate from lakes and streams. Okay? Or it can evaporate from plants. Okay? As they carry out what process? Photosynthesis. We call that transpiration or evapotranspiration. Okay, transpiring, they're giving it off as a result of another process. It's not just evaporating from their surface. Okay, it's being given off as a result of photosynthesis. So 2 ways that water can become a vapor and get up into the atmosphere. Okay, once it gets up into the atmosphere, okay, it's water vapor, but it condenses and it can fall as snow, hail, okay, rain, whatever. Okay, and then when it gets onto the surface, it can run off. I know it's hard to see that there. Okay, so any water, okay, that lands on the surface can be absorbed, but it can also run off, and the majority of it, realistically, runs off. Okay, so that gets into rivers and streams, which eventually ends up back in the ocean. Sometimes it gets trapped. Okay, it gets trapped in a lake or something like that. We call that freshwater storage. Okay, or the other process that can happen is this one. Infiltration. Okay, infiltration is the process of water being absorbed into the soil. Okay, and when it does that, it, like, if you've ever made coffee, okay, and not with like a Keurig or a Tassimo, like the old-fashioned kind where you put a bunch of grounds in the paper filter, okay, water percolates, okay, down through the soil. That means moves through the soil particles in the same way that water moves through the coffee grounds when you make coffee. Okay. Well, when you put water through coffee grounds, does it change color? It becomes coffee, right? Well, water does the same thing as it moves down through the surface or through the soil. It picks up minerals and things like that. Okay, that stuff can get down into what we call aquifers, okay, or the water table, okay, where it would be filling up people's wells. If you live on a farm, maybe you have a well, okay, that you draw your water from. Okay, that's how those get filled in. Okay, is through this process of infiltration. All right. That's all of it. Infiltration, runoff. Yeah. Okay. I might put that as a multiple choice set of questions on an exam. All right. 97% of the Earth's water is salt water. That sucks because we can't drink that. Okay. We have to survive on the other 3%. Unfortunately, 3/4 of that 3% is frozen. So that means all the fresh water that we require is less, okay, than 1% of the remaining water on Earth. Okay, every river, every lake, okay, on Earth adds up to less than 1% of all the water. Gives you some idea how much is in the oceans. Okay, so we got also obviously glaciers and things like that that hold fresh water. We depend on that in our area because that's what feeds our rivers and streams. Okay, but there's a lot of water in these. Okay, but what's happening to it? What's happening to all of our glaciers? This is a glacier in case you couldn't tell. Yeah, they're receding, they're shrinking. Okay, they're slowly melting. Now, a lot of people want to blame that on all the stuff that we do. Okay, certainly we're a little bit at fault, but glaciers have been receding for like the last 10,000 years. Okay, we haven't been driving cars that long. All right, but they've been receding for that long. Okay, now to give you some idea of the amount of recession that is taking place here. Okay, this is the Robson Glacier. Now, you can see the valley walls on either side here. Okay, so here's a valley wall. Okay, there's kind of a valley wall over here as well. Okay, the glacier used to fill that whole valley. So they're not just getting shorter, they're also getting smaller. Okay, like their depth is not as great. Okay, when we were my dad and I were hiking in this area. Okay, we hiked from all the way down, like way down here. I think I told you this back in when we talked about the altitude. Okay, being a factor affecting climate. Okay, so way down in here was where we had started. And we walked past this sign that said, in 1901, the Alpine Club of Canada marked this point as the foot of the Robson Glacier. We couldn't even see the glacier standing next to that sign. Okay? We had to walk another kilometer before we could get to the glacier. The glacier in 100 years had receded 1 kilometer. Okay? So it's a lot. Glaciers are shrinking. Okay? But once in a while we get a cold year and they expand a little bit. Okay? But in general, yes, they're getting smaller. Okay? Everybody with me there? Right? But they still represent a very large amount of fresh water. Okay? And obviously they provide that fresh water, but that fresh water eventually ends up back in here. All right, questions there? All right, the lithosphere. The lithosphere is all of the rock, all of the earth, okay, the solid parts, okay, because litho means stone, okay, so this is representing essentially all the solid parts of the earth. Now, we said that the atmosphere transfers most of the thermal energy on Earth. The hydrosphere has some part to play in that. It provides the water that makes up for latent heat. How much energy, suppose, is transferred through the Earth's crust? Not very much. Okay, it's just not very fluid because it's a solid. It's not very fluid because it isn't a fluid. It's a solid. So it can't flow, which means it can't transfer energy by the most efficient means possible. What are the 3 ways to transfer energy? Anyone remember from like grade 9? You guys heard of those 3 terms before? Okay, conduction, convection, and radiation. Okay, radiation is how energy gets to the Earth. Okay, it travels in waves all the way to the Earth. Okay, from the sun. And there's some places on Earth right now. You guys are radiating energy away, okay, as heat waves, okay, away from your body. All right, convection, okay, is moving fluids being able to transfer energy. So hot air rises, cool air descends. Okay, that's convection. Ocean currents are convection. Okay, anything that is a current. If you have a convection oven, it's got a fan inside that makes the air circulate so that all parts of the oven are an even temperature. Okay, and then lastly is conduction. And conduction is how energy is transferred through a solid. It's very slow and it's very inefficient. Okay, solids are more likely to radiate energy away than they are to conduct it over long distances. Okay, so conduction happens. Okay, so if I have a solid material here and I'm heating this end of it, okay, we got all the little atoms, okay, inside. When I heat this side here, the atoms start to move faster. And when they start to move faster, they run into each other more often. But because they're so tightly packed, they can't change places. And so as they vibrate back and forth, they bump into each other, and this one vibrates a little bit more, and this one vibrates a little bit more. That process very slowly transfers heat along the length of the solid material. Okay, are some materials better at transferring energy by conduction than others? Yes. Okay, things like metal generally are very good conductors of heat. Okay, doesn't mean it happens really fast, but it happens faster than it would in something like plastic or wood. All right, which is usually why we have plastic or wood as handles on our cooking utensils. Okay, if you leave, a metal spoon in a pot that's cooking for very long, okay, pretty soon you won't be able to grab the end of it. Okay, everybody with me there? All right, so it's the lithosphere is not as important in terms of transferring energy, but it is important in that it gives a place for the plants who are converting our solar energy into nutrients and stuff, okay, to live. Without the crust, there wouldn't be any of that. All right, so the lithosphere basically has layers, which we'll talk about here in a minute. It's the topmost layer, okay, of it is called the soil. Right, and that's where plants can grow. What's soil made out of? Okay, what's dirt made out of? What's that? It's made out of dirt. Okay. Well, it's actually decomposed, partially broken down rock. Okay. The soil that we grow things in here is the result of rocks breaking down slowly over time. The process of building soil takes a very, very long time because rocks have to break and wear and weather, okay, so that the particles get smaller and smaller and smaller and eventually accumulate as dirt. Now, that's not the only part of dirt. That's the gritty part of dirt. Okay? The other parts of dirt are decomposed organisms, organic material, litter, okay, things like that, okay, that make up, and I mean plant litter, not ignorant litter, okay, people throwing garbage. Okay? All of that eventually makes up the soil. Okay? So it's its own ecosystem. It's composed of living and non-living things. Okay, chemicals, air, water, decaying material, and obviously bacteria and other living organisms within it. Now, looking at this picture here, does this look like soil? It's just rocks, right? Is there something growing in it? Then it's soil. Okay, you'd be surprised what can be considered soil. Okay, that can be considered soil. Is it very good? No. Would you grow crops in it? No. Okay, but some things can live in it. All right, any decomposed rock is soil. All right, soil is typically divided into horizons. When you're a kid, I'm sure you dug a hole at some point. Okay, or you've at least seen a hole dug. Okay, what's the hole's natural enemy? No, that's what makes a hole. No, the pile, because the pile can fill the hole. See? Okay. Anyway, okay, so your soil is divided up into essentially 3 layers. The A horizon, the B horizon, and the C horizon. Okay? The A horizon is your topsoil. That's typically where things are growing, where you've got organic material, lots of moisture, things like that. The B horizon is your subsoil. So when you dug that hole, what did you hit after a little while? Clay. Yeah, okay? There's a reason for that. Clay is made up of really, really fine particles. Okay? They're much smaller than the particles that typically make up the A horizon. So when there's moisture, the moisture can wash the small particles through the larger ones, and they accumulate underneath. Okay? That sort of makes sense to everybody? Okay, so the smaller particles wash through the larger ones and they collect underneath. Okay, they also, because they're small, have a tendency to cement themselves together. Okay, the clay was often quite a bit harder to dig through, okay, than the soil, loose upper soil was. Okay, so typically you see kind of a layering like this. You'd see your topsoil, okay, which would be kind of, use a different color. Okay, kind of right in here. That would be your A horizon. It's kind of thin in this soil. Okay, and this would be your B horizon in here. And then underneath that would be your C horizon, which we call sometimes parent material. Okay, because this is the stuff that's breaking down and becoming soil. All right, so it's giving rise to the soil like your parents gave rise to you, parent material. All right. So the A horizon, like we said, okay, is a mixture of decomposed rock, living organisms, and decaying organic matter. Some places have thicker A horizons than others. Okay, here on the prairies, we typically have fairly thick A horizons. Okay, there tends to be grass tends to build up an A horizon quickly because every year the grass dies and new grass grows up from underneath. So there's always a layer, okay, of stuff that's going to decompose and provide more organic material. Okay. In other places, there's very little A horizon. If you go into the mountains near the tree line, okay, the soil gets thinner and thinner and thinner. What about tropical rainforest? Would it have a very thick or a very thin A horizon? Actually, it's almost absent. Weird. Okay. In the place that has like basically the most lush growing plants, there's almost no topsoil because it's always washed away by flooding. Okay, so the plants actually gain most of their water and nutrients out of the floodwaters. They can grow even if their roots are submerged. Not something plants around here can do. Okay. So this would be a soil that's more typical of where we live. A thick A horizon, a thin B horizon, and then under that you would start hitting rocks. Okay, around here, okay, you'll start hitting rocks after you've dug, well, depending on where you are in town, okay, after you've dug maybe about 1.5 to 2 feet. You'll start hitting rocks. Not saying that you're hitting solid rock, but you'll start hitting rocks. Okay? There are places in town where after digging 1.5 feet, you will hit the bedrock. Okay? And what's the bedrock made out of around here? Anybody know what kind of stone? It's actually sandstone around here. Our bedrock is made out of sandstone. Okay, and there are certain places in town where there's outcroppings of it, and they are very close to the surface. Okay, and in other places you could dig 2.5, 3 feet, okay, before you would hit it. All right, the B horizon, okay, is little or no organic material. Rock is less decomposed, so there's going to be chunks of rock kind of in the B horizon, okay, and there's lots and lots of clay. So you can kind of see that in this picture here, okay, that it's almost all kind of that reddish color. Okay, around here our clay is actually a little grayer, okay, but most clay is kind of red. Okay, this would be what a tropical rainforest soil profile would look like. A horizon is very, very thin. Okay, you got a very, very thick B horizon. The clay, that's actually what the plants anchor into, and then underneath that would be kind of worn and weathered parent material. Okay, and then the C horizon, like we said, composed of parent material. So, okay, you can see here, this would be kind of in the foothills, all right, kind of a soil profile. So you got an A horizon that runs from about here to about there. Okay, then you got your B horizon running to about here. Okay, you're starting to get chunks of rock in there, and then this would be your sandstone kind of bedrock outcropping underneath. Okay. Questions on that? All right, so the Earth's a system. Okay, and so there's interacting parts of it. Okay, the input for that system is the sun. It's plain and simple. There isn't any other input of energy for the Earth. All the Earth's energy comes from the sun. Okay. We get reflected, we get re-radiated energy. That's the stuff that bounces off the greenhouse layer and things like that. Okay. So what we're looking at on a typical day is this. Here's our 100% incoming radiation. Okay. About 16% of it gets absorbed, okay, by the atmosphere, water vapor, dust, carbon dioxide, things like that. Okay. About 3% of it gets absorbed by clouds. Obviously not very much, because clouds are what color? White, typically, especially on the top. Okay, and then about 51% of it is being absorbed by land and water. Okay, now along the way here, you'll notice that doesn't add up to 100%, right? Okay, along the way, okay, we got 6% scattering by the air that makes our sky blue. Okay, we've got 20% reflected by clouds, and then we've got another 4% or so, okay, reflected by water and land surfaces. Okay, so there's a fair amount of reflection going on there. Okay, that outgoing radiation, okay, so this kind of stuff here, this outgoing amount. Okay, some of it gets absorbed by water vapor on the way out, which leads to the atmosphere warming up. Anything that's absorption leads to warming up. Okay, and then we've got emission by clouds, okay, and things like that that are showing kind of our energy being lost, okay, or going away. All right, so like we said, the main input of energy for our global system here is the sun. Gravity, magnetism, and geological forces are negligible by comparison. Okay. All right, now we talked about these things here: convection, conduction, and radiation. Okay, we want to be able to harness those as much as possible. Make them do work for us. Okay, I should say we want them to do heat for us, but it never sounds right when I say that. Okay, we want them to capture and transfer solar energy where we want it, or thermal energy where we want it. So convection, obviously, how do we see convection happening on Earth? What's the evidence that there's moving fluids on Earth? Okay, to some extent, although clouds represent more of the latent heat, the water vapor being present. Wind. Wind is the evidence that air is moving. When air is moving, there's convection, because it's a moving fluid. When air moves, it carries masses from one place to another, and it thus carries energy from one place to another. Okay, so wind is necessary for energy to be transferred properly. Okay, we also see, like we said, ocean currents, hot air, movement of the water from place to place can carry energy from warmer areas to cooler areas. Okay, convection is obviously always carrying energy from warmer areas to cooler areas, but it can't all move from the equator to the North Pole, because then what would happen? If energy only moved in one direction, from hot to cold on the Earth's surface, what would there be none of at the equator anymore? Not just heat. There'd be no air either. Okay, I mean, if all the hot air just went, oh, well, we got to go to the North Pole because it's cold there, there'd be no air at the equator. Okay, it's got to be cyclical. All right, so it's a convection current. All right, we get wind moving in certain directions. We're going to talk about that more tomorrow when we talk about wind patterns. Okay, but understand that when hot air moves in one direction, cool air is displaced. Okay, by that warm air. All right, so in your house, we take advantage of that. On the main floor, where are your heating ducts? Ceiling or floor? Floor. The little grates, right, that blow hot air, you probably stood over those at some point. Okay, they're on the floor. There's a reason for that. It makes the most sense to put them on the floor. Okay, because we want the hot air to first encounter the cold air, and the cold air is always near the floor. Okay, so hot air is going to rise past that cold air out of the ducts. Okay, and obviously your furnace has a big fan that helps that process. Okay, and forces it up and around. We want the air to move. Okay, way back in the day when people heated their house with hot water heating. Okay, you just had a big radiator. Okay, something you had kind of one in each room. Right, didn't have a fan or anything. It just radiated heat. So if you stood next to it, you cooked. If you stood on the other side of the room, you froze. Okay? It wasn't very efficient because it was only using radiation to transfer energy from one place to another. Okay? A forced air furnace is much more efficient, okay? Because it actually forces the air to move and transfer the energy more efficiently. Okay? Does everyone kind of follow me on that? Okay? Anyone have one of those like old radiators or seen one of those? Okay, you don't see them around very much anymore. They don't use them very much. They were annoying as all get out. Okay, because when you crank them open, you had like no control. It was either on or off. So you'd often have it on with the window open. Okay, otherwise your room would get cooking hot. Okay, yeah. So they weren't a great way to heat. It was heat, but it wasn't a very efficient way to do it. All right, so that's using kind of radiation. Okay, radiation is obviously energy moving, okay, by waves, and that's how you would feel it. I mean, if you're next to a fire or you're next to, you know, something like that, you can feel the waves of heat, okay, coming at you. That's thermal energy moving by radiation. Okay, grabbing something that's hot, okay, or grabbing something that's cool on one end and hot on the other. Eventually, energy will transfer by conduction. The moving particles, okay, will run into each other enough, okay, that the heat will get to the other end. So those are the three methods. We want to sometimes we want to harness those, and sometimes we want to prevent them. Okay, if we want to prevent them, what are we doing? Preventing the movement of energy is called insulating. Okay, do we do a fair amount of that here? Okay, do some materials insulate better than others? Okay, we've said snow's a good insulator. Okay, snow has only one drawback as an insulator. It melts. Okay, and then it's wet, and then you're cold again. All right, so there is a drawback to snow. Snow's a great insulator. Okay, as long as you have the ability to keep yourself warm around, you know, the kind of 5-degree mark or so. You can get a Quincy up to 10 inside, but they'll start to drip on you. Okay, at that point, just from your own body heat. Other materials obviously work very well. What are some materials that are very, very good insulators? Rubber is a good insulator against electricity, but not against heat energy. No, glass is not a good insulator. Again, a good insulator against electricity, but not against heat. I mean, think about it. If you put a cold liquid in a glass and you put your hand around it, does your hand get cold right away? Yeah, because your energy transfers through the glass very easily. Foam, yeah, foam can be a good insulator because what's trapped inside of it? Air. Okay, it prevents air from moving. Okay, and anytime you can prevent air from moving, you prevent this. Okay, and this is the main way that energy is lost, is through convection, through moving air. Okay, that's why we always, you know, if you open the door, okay, and someone's saying close the door, you're letting all the heat out. Well, you are. Okay, the heat is very rapidly convecting out of your house, okay, when the door is open. So we keep the door closed to prevent that convection. Okay, within your walls. Okay, so let's say this is inside, this is outside. You've got your fiberglass insulation, right? Has anyone ever seen fiberglass up close? Okay, you don't want to get it on you, okay, because the little glass fibers get in and you can't get them out. They break off and they're very itchy. Okay, whenever you apply it or use it, you should wear a mask because you don't want to inhale them. Okay, it can be very bad for you. All right, but it's a great insulator. Okay, because within all these little fibers is trapped air. So you've got warmth in here. When the warm air hits the interior wall of your house, it wants to try and move out to here because heat always wants to move from hot to cold. But when it gets to the wall, usually your walls are painted a kind of a lighter color, and lighter colors will reflect the heat energy a little bit. Okay, but any energy that gets through your drywall will get to here, and the only way for it to get to the outside is for it to move. But the trapped air there prevents any currents from being set up. Okay, if you have a wall without any insulation in it, okay, the heat will get to here, it'll rise, okay, and it'll start moving towards the outside, and you'll get a convection current getting set up inside of your wall. And that's just eventually going to transfer all of your energy to the outside. Okay? Everybody with me there? Okay, now we had mentioned that we thought glass was a good insulator. Where does your house lose most of its energy through? Through your windows. Okay? Because your windows can't reflect any energy, and it's harder to insulate them. Okay? If you insulate them, they will no longer be transparent, okay, and thus defeating the purpose of having a window. All right, but there are ways to make windows more efficient. If you get low E windows, they're 2 panes of glass. Okay, and what's inside? Nothing. You make it a vacuum. Okay, if you can make nothing in here, nothing can move. Or sorry, nothing can't move. I know this doesn't make any sense, but if there's nothing in there, there's nothing that can get moving. You can't get a convection current set up in a vacuum because there's no particles that can move and carry the energy away with them. All right, insulated thermoses like this one. Okay, that's how they set them up. Okay, in between the outside and the inside is a vacuum. Okay, they actually suck all the air out and then seal it. Okay, because there's a vacuum in there, there can be no convection happening in that vacuum because there's no matter in there that can get moving. All right, make sense? All right, what are some other materials that are good insulators? We've got fiberglass, we've got snow. Okay, we've said that a vacuum can be a good insulator. What are some natural insulators? Wood's okay, but it's a solid, and it will eventually transfer energy through, but it's not bad. It's better than metal. Wool. Okay, anything that an animal would use to keep warm, okay, hair, feathers, all that kind of stuff, they all work on the same principle. Okay? Why is wool a good insulator? Well, have you ever looked really closely at wool? It looks like fiberglass. Okay, it's all thready and whatever. There's lots of trapped air in there. Okay, so when it traps air, it can keep you warm. Feathers, same thing. Okay, geese and ducks, they have different kinds of feathers. They got the downy feathers that are kind of on the inside, and they trap air. And that down is one of the best insulators you can get. That's why sleeping bags and really high-end coats are filled with it. Okay, because it traps air, and it's a great insulator even when wet. All right, lots of our synthetic insulators are good until they get wet, okay, and then they're not a good insulator. Cotton, great till it gets wet. As soon as it's wet, what happens to it? It shrinks, all the air spaces are gone, and you're cold. Okay, everybody with me on that? Okay. All right, if you want to keep warm, you go outside in the wintertime. We always say you should dress in layers. Why is layering a good idea? Makes air pockets. Okay, it's got layers of trapped air. The other reason dressing in layers is important is if you get moving, you start to warm up. What do you not want to do if it's really cold outside? Sweat. As soon as you get wet, the insulative value of whatever you're wearing is going to decrease. By dressing in layers, you can take layers off, okay, keep them dry, keep yourself dry, and then put them back on, okay, as need be. All right, so all these things are important in terms of kind of staying warm and defeating these things. Now, how do we prevent radiation? I mean, if we have a vacuum or we've got, you know, fiberglass and things like that, we're stopping convection. Okay, how do we stop radiation? Okay, you're thinking of the like X-rays and gamma rays. Yes. So if you go to the dentist, they always say, "Okay, put this in your mouth," and then they go hide. Okay, they're usually hiding behind a lead wall. Okay, I don't mean insulate against that kind of radiation. Thermal radiation is more what I'm looking at here. Okay, so lead will absorb, yes, short waves of radiation. We're talking about long wave radiation, your thermal. Okay, if I want to keep that in, I want to. What did the snow do? It's really light in color, so it reflects. Okay, we want to reflect radiation back. Okay, inside of a thermos will usually have a reflective surface. Okay, and so it'll reflect a lot of that energy back. You know, you put light colors on, light colors will reflect your heat back to you. Have you ever seen one of those survival blankets? Okay, they're basically like a sheet of tinfoil, right? And so if you wrap yourself in that, the shiny side, okay, will reflect your heat, your radiant energy back at you. Okay, how many people have seen tinfoil up close? Okay, use tinfoil. You ever notice it's different on both sides? Why is that? You're going to learn a valuable lesson, so you will not be humiliated at a barbecue. Right. The other side is dull. Okay? The dull side absorbs energy. The shiny side reflects energy. If you're going to put a baked potato on a barbecue, and I see people do this all the time, they just grab tinfoil and wrap the potato. They got 3 potatoes wrapped shiny side in, 3 potatoes wrapped shiny side out, because they don't know that tinfoil has 2 sides, and the 2 sides serve different purposes. Okay? When I go to a barbecue, I always watch for that. I want the ones that are wrapped with the dull side out, because I know they're going to be cooked when I eat them. Okay? If you throw a baked potato or a potato wrapped in tinfoil on the barbecue with the shiny side out, it will not cook. Well, it'll eventually cook, but it won't cook very fast because you've put the reflective side out. And so all it's doing is reflecting all the radiant energy from the barbecue away from the potato. Okay? If you wrap it the other way, it absorbs energy, it goes into the potato, through the potato, hits the shiny side and goes back through the potato again, cooking it way faster. Tinfoil has 2 sides, people. Okay, make sure you don't embarrass yourself at a barbecue, or you can look like the smartest person at the barbecue, because I'll bet you 75% of people do not know that. Okay, probably a lot of you didn't know that until right now. All right, there you go. So those are some ways. Radiation, the way we either want to make something dark to absorb it, or we want to make something light to reflect it. Okay, now what about conduction? How can we prevent heat loss by conduction? How do I make sure energy doesn't get away, okay, by conduction? Well, in order for energy to conduct, solid surfaces have to be touching. Okay? Conduction can only work if the molecules can run into each other. So the less points of contact I have, okay, the less conduction there will be. All right? On a really cold day, you can try this at home. Go to an exterior wall in your house on a cold day, okay, and run your finger along it. And you'll find cold spots about every 2 feet. Noticeably cold. It's got to be about minus 30, minus 35 outside for this to work. Okay? But if you run your finger along, okay, you'll find cold spots about every 2 feet. Okay? Reason being, the frame of your house is built like this. And every 2 feet, there's a stud. Okay? A stud is a board, okay, that holds up the wall. It touches both the inside wall and the outside wall. Okay? And it is a point where conduction of heat can occur through from the inside to the outside. These areas here, the spaces in between, are filled with insulation, hopefully. Okay? If they're not, all of your wall is going to be very cold. Okay? But you'll notice that there'll be a couple of cold spots, okay, along the length of that wall. It's got to be really, really cold outside for that to work, okay? But it does. All right, so conduction, to prevent it, we want to eliminate points of contact. Okay, we do that by not making our wall one solid piece. If it was one solid piece, we wouldn't be able to insulate it, and there'd be direct conduction between inside and outside. Okay, does that sort of make sense? Right. Yes. All right. Atmospheric transfers. So transferring energy on Earth Most of that happens within the atmosphere. Okay, so it's the most important part in terms of transferring energy. All right, so this is energy transfer by conduction. Is that going to happen within the atmosphere? No, because the atmosphere is fluid. Okay, it's not solid. Okay, this is showing here that when I heat up one end, the molecules move faster. Okay, whereas down here they're not moving as fast, so it's not as hot down here. Okay, here's that radiator thing I was telling you about before. All right, the hot air would rise above the radiator and descend, and then you kind of get this going, but it didn't effectively heat the whole room because not all the air in the room would move. All right, it's still a convection current. Okay, it's still movement of air. Okay, because of differences in energy. Okay, this is showing it kind of in an earth environment or an outside environment. You got energy coming in, hot air rises. Okay, and as it rises, okay, it gets lighter. It's more buoyant. Okay, the cooler air is heavier and less buoyant, so it moves down. Okay, and then you get this kind of process occurring. Okay, over the course of the day. If you're near the ocean, you'll get what's called a sea breeze. So here's the ocean. Nice waves, right? Okay. And then here's the Earth. That's a tree. Okay. Now, what happens during the day is the land heats up faster than the water. Okay, water just doesn't heat up very fast, whereas the land does. Okay, this has got a lower albedo. It absorbs more energy than the water does. So the air above the Earth heats up faster, and it rises. Okay, as it moves away, cool air from above the ocean rushes in to replace it, and you get what's called a sea breeze. Okay, and so you get a circulation of air. Okay, this hot air rises, but it can't fall back down because the cool air moved in to replace it. There's your convection current. Okay, later on in the day, the situation reverses. Okay, after the sun goes down, the land cools faster than the ocean does, and air above the ocean rises, and you get a land breeze, which is air blowing off of the ocean, or off of the land, sorry, and onto the ocean. All right, and then we got our radiation here, radiant energy in this bottom right diagram. Okay, so it comes in, hits the Earth, okay, and is either absorbed or reflected. So the atmosphere, okay, local and regional winds and convection currents. Okay, and air masses carry energy as sensible heat and as latent heat. That's if they're carrying any water vapor, they're carrying latent heat with them. Okay. All right, questions on that? Okay, water condensing in the atmosphere releases latent heat. So we talked about this. This is the hydrosphere now. Okay, so hydrologic transfers have to do with water. Okay, latent heat is that energy that is absorbed by water as it changes state. You can't sense latent heat. Okay, you can't feel it. You can only know it's there when it is changed back into sensible heat, when either water vapor condenses back into liquid water, or when water freezes into ice. Okay, anytime there's a state change, that latent heat gets released. All right, we'll talk more about this when we talk about latent heat later on in the week here. But okay, if you put ice into water, what happens to the temperature of the water? It goes down. Yeah, it wasn't a trick question. It goes down. Okay, what happens to the temperature of the ice? No, it doesn't. No. It stays at 0 degrees Celsius until all of it's melted. Okay? Ice will not exist above 0 degrees Celsius. Okay? I mean, the air temperature might be higher than 0, but the ice will not be more than 0. Ice can't exist above 0 degrees Celsius. Right? But it takes a while, even if the surrounding air is more than 0, for all of the ice to melt, because it takes a lot of energy, okay, that latent heat needing to be absorbed, okay, in order to change the state. Okay, it takes even more to evaporate liquid water into steam. All right. Okay, so this is kind of the latent heat diagram here. Okay, so you've got if you heat up ice, okay, then you're putting energy from the environment into the ice, and it'll melt and it'll become liquid. If you heat that more, okay, then it'll evaporate and become a vapor. If you cool the vapor, okay, it condenses back to a liquid. Okay, if you continue to cool the liquid, it freezes back into a solid. Okay, now these ones you don't see very often, but if you were to vaporize ice, okay, which can happen on very rare occasions, we call that sublimation. It doesn't happen with actually with water very much, but happens with carbon dioxide. Okay, you never see carbon dioxide as a liquid. It goes directly from solid to gas. Okay, that's why dry ice makes smoke. Okay, if you pour a little bit of water on dry ice, it just gets all smoky. Right? So that's sublimation. The opposite of that is deposition, and that's where you get like carbon dioxide frost. Okay, like happens on Mars. Okay, that's how they get a lot of their snow is actually dry ice, carbon dioxide ice that has gone from vapor directly to a solid. All right. Okay, and then in the lithosphere, okay, on land, most of the energy transfer is by conduction, okay, which, like we said, is very slow. The land's role is mostly to provide nutrients and a base for the plants to grow in. Okay, the land also influences how much energy is absorbed and then can be later transferred back to the atmosphere, okay, through albedo. All right, I think that's it. Okay, is that making sense to everybody? Okay, in terms of, there's a lot of information in that lesson. Okay, we do a lot of application stuff with the information in this lesson: the conduction, the convection, the radiation. Okay, the how the atmosphere moves. There's going to be a lot of questions that ask you that are situational. Okay, here's a situation. Explain how this is showing energy being transferred. What process? So is it convection, conduction, radiation? So that's the kind of thing to expect testing wise, okay, from this lesson, is a lot of real world application type of questions, okay, where you'll have to explain and evaluate and stuff like that. All right. Okay. You have your climatograms coming up due here, guys, on the 8th. Okay, so make sure that you are getting together with your group. Okay, if you still need to do that, hopefully you just shared your climatograms with everybody and you were all able to get it done. Okay, but make sure you have those done for January the 8th. Okay, and that's probably the last thing that will actually be for homework. Okay, for you. We're going to do a little kind of mini lab with latent heat and melting ice and stuff like that, but we'll get it all done in class, so it won't be a homework thing for you. Okay, so what again should you be doing with your time? Yeah, okay. Don't go home and tell mom and dad, I don't have any homework. Mr. Codere isn't assigning me anything anymore. I did. I'm assigning you stuff. Okay, I'm telling you, start studying for your final exam. Okay, get your stuff together so you're organized and ready to go for that. All right.